Hello everyone, welcome to ACE Engineering College YouTube live session. Myself, Dr. C.H. Srinivasa Rao, working as professor in the Department of ECE of ACE Engineering College. In this session, I am going to discuss a topic called multistage amplifiers in the subject analog and pulse circuits. Of course, in J&T University, this subject is named as analog and pulse circuits. In some other universities, this subject is also named as electronic circuit analysis, analog electronics, analog circuits, and so on. The topic for today's session is multistage amplifiers. Before we talk about the analysis of multistage amplifiers, first of all, two basic questions that arise from our side are what is a multistage amplifier and why we need multistage amplifiers. That is, first question is, what is a multistage amplifier? To understand this, just look at this. If n number of individual amplifiers are connected in series, or more technically speaking, if n number of single stage amplifiers are cascaded, the resultant amplifier is called as multistage amplifier. Look at this slide. This is amplifier 1, this is amplifier 2, and so on. You can have n number of amplifiers to be cascaded so that the resultant amplifier becomes a multistage amplifier. Now, why we need multistage amplifiers? When already there are single stage amplifiers available, why we need multistage amplifiers? To understand that, first of all, look at the outcome of this multistage amplifier. Once if we cascade n number of amplifiers, the overall gain of the multistage amplifier A becomes product of gains of individual stages. That means A1 into A2 and so on into AN is the overall gain of a multistage amplifier. That means what? Basically, multistage amplifier is a high gain amplifier. Now the question arises for us is, will high gain reflect on high output voltage? That means, now let us consider a simple example here. Assume that 3 CE amplifiers, 3 common emitter amplifiers having gain of 100 each are cascaded to form a multi-stage amplifier. Then the overall gain of the 3-stage amplifier becomes 100 into 100 into 100. Means the overall gain becomes, let us say, A equal to 10 power 6. If overall gain of a multi-stage amplifier is 10 power 6, then the resultant output V0 in an amplifier, general formula for V0 in an amplifier is V0 equal to AVI is the formula. Suppose if A is 10 power 6 and if VI is, let us say, 1 volt, can we get 10 power 6 volts of output? That is the question here. Can we get 10 power 6 volts of output from a multi-stage amplifier which is having a gain of 10 power 6? Absolutely no. This is absolutely wrong. Why? Because the maximum possible output in any electronic circuit, doesn't matter whether it is a single stage amplifier or a multi-stage amplifier, the maximum possible output will be less than or equal to the supply voltage we connect in the circuit. That means, suppose if 12 volts of power supply is connected in your amplifier circuit, getting an output of around 10 volts is meaningful. Expecting output beyond 12 volts is meaningless in electronic circuits. Now, let us assume the maximum possible output in the circuit is, let us say, 10 volts. Then, what is the significance of this 10 power 6 gain? Where it reflects on? To understand that, let us rearrange this formula for VI. VI equal to V0 by A is the formula, which will help us to understand the significance of multi-stage amplifier. Now, already we observed that maximum possible output is 10 volts. A is 10 power 6. Then what it will be? Around 10 microvolts. That means what I am trying to convey to you with this simple example is high gain in multi-stage amplifier will not reflect on high output voltage in the range of thousands of volts. It will reflect on amplifying very weak signals in the range of from the range of microvolts to volts. So conclusion is basically multi-stage amplifier is a high gain amplifier. That high gain will not reflect on thousands of output voltage, thousands of volts as output voltage. Maximum possible output voltage is always restricted to 10 volts or maybe 12 volts, or let me say less than or equal to supply voltage. Then with that very high amount of gain, what we can achieve in multi-stage amplifiers is we can amplify very weak signals which are in the range of microvolts to a range of up to a range of volts. That is understandable. Why? Because in real time scenario, in every natural source signal is very weak in amplitude. Therefore, to amplify that very weak signal to a certain level of amplitude, multi-stage amplifiers are mandatory. High gain multi-stage amplifiers are mandatory for us. The best popular example of multi-stage amplifier is operational amplifier or op-amp. Now, let us see one of the frequently asked question in various university examinations. The question is, explain the merits and demerits of various coupling schemes used in amplifiers. Now, if you look at this simple block diagram of multi-stage amplifier which I have shown in this slide here, when we are cascading stage 1 and stage 2 here, stage 2 is connected or coupled to the stage 1 by means of a coupling device. We have to use a coupling device to interconnect different stages of amplifiers. Depends upon the type of coupling element used, there are 4 coupling schemes proposed by the designers. They are direct coupling, second one RC coupling or capacitive coupling, third one transformer coupling, and fourth one tuned circuit or inductive coupling. Now let's consider one by one and let us try to discuss about their merits and demerits. First, let us start with direct coupling scheme. Yeah, look at this diagram. See, if you carefully observe, the output of stage 1 is connected to the input of stage 2 here. If you look at the connection between two stages here, the output of stage 1 is connected to the input of stage 2 directly, hence the name direct coupling scheme or direct coupling is given for this. The most popular circuits in which direct coupling scheme is implemented are Darlington pair amplifier and operational amplifier. These two are the most popular direct coupled amplifiers. Now, let us consider the advantages of this circuit one by one. First advantage, DC signals can also be amplified. Understandable? If you apply input signal as DC here, that DC signal can be directly enter into the first stage as there is no coupling capacitor used, as there is no blocking capacitor used. Whatever the DC, in case if you apply a DC input here, that DC input can directly enter into the amplifier and gets amplified in the first stage. That amplified DC will be directly entering into the next stage. Again, since there is no blocking or coupling capacitor in between the two stages, direct coupling mechanism is implemented. Therefore, the output DC current of first stage can directly enter into the input of second stage. As a result, it can get amplified in the second stage also. And if you finally observe, the output of second stage is directly connected to the load. That means the amplified DC current of second stage can be directly fed into the load. As a result, from source to first stage, from first stage to second stage, from second stage to load, continuously direct coupling is implemented by us. The DC signals, when whenever it is required to amplify, it can be comfortably amplified in this amplifier, direct coupled amplifiers. Second one, large bandwidth. Of course, if you consider the frequency response of this amplifier, look at the frequency response of this amplifier here. Since there is no coupling capacitor or blocking capacitor used in the circuit, signals right from f equal to 0 will be amplified in the circuit. So the frequency response of this amplifier can be shown like this. That means what? What will be the bandwidth of this amplifier? Large. Right from f equal to 0, signals can be amplified. That's why bandwidth of the amplifier will be large. Hence, these amplifiers are considered to be large bandwidth based amplifiers, generally used in wideband amplifier applications. Next, since no coupling element is used in the circuit, of course, the circuit is cost effective. Understandable? No additional coupling element is used, no coupling capacitor, transformer or inductors are used here, only direct coupling mechanism by means of a connecting wire we can implement the circuit. Therefore, the implementation cost of the circuit is very less, hence it is considered to be cost effective. These are the basic advantages of this circuit. However, this circuit suffers so many drawbacks. Let us consider those drawbacks one by one. The first one is the most important disadvantage of this circuit is improper isolation of DC conditions among the amplifiers. That is, look at the situation here. The DC output current of first stage, some of the DC output current of the first stage may be entering into the input of next stage. Already we maintain DC conditions for individual amplifiers at the time of design of the amplifier itself. Each amplifier will have its own DC conditions. But when we cascade these amplifiers by means of direct coupling here, unfortunately, some of the DC current of first stage may mix with the DC current of second stage, which will disturb the DC conditions of second stage. And that will again reflect in the third stage and so on. As a result, overall, in the overall amplifier, the DC conditions of individual stages are going to be mixed and leads to lot of disturbance in the DC conditions. So, that means since there is no coupling capacitor placed in the amplifier circuit, in the total amplifier, DC isolation is not done. Means the DC currents are not properly separated. As a result of this, the disturbance to DC conditions of stage 1, disturbance to DC conditions of stage 2 and so on. Where it reflects on? It will reflect on the second drawback. The overall operating point of the amplifier becomes unstable. If operating point of the amplifier is unstable, where it reflects on? It leads to unfaithful amplification. Let's see why operating point is going to be disturbed in the direct coupled amplifiers. We know in each amplifier we maintain certain amount of DC current, DC base current, which leads to the establishment of quiescent collector current in the circuit. For example, let's see. This is, let us say, IBQ1 is the DC base current we maintain at the base of Q1, which will automatically establish a collector current called ICQ, one of the most important coordinate of operating point. Similarly, we maintain base current of IBQ2 for second transistor Q2. This will help us to establish a quiescent collector current of ICQ2 as one of the important of operating point coordinate. Now, the problem in this circuit is, because of direct coupling, some of the DC output current of first stage may mix with the base current of second stage, which leads to a change in base current of second stage, which will automatically change the collector current of the second stage. If collector current of the second stage gets modified, that will automatically reflect on shift in operating point. Operating point may shift towards saturation region, which will automatically leads to clipping of the output signal in the positive half cycle, which leads to unfaithful amplification in the amplifier. That's what the second most important drawback of this circuit. Third one, noise or DC signal amplification during AC signal amplification. This is another basic problem we notice in these direct coupled amplifiers. For example, Instead of DC amplification, for DC amplification, assume that this amplifier is used for AC signal amplification. We know AC signals are arriving from natural sources. In case, by mistake, if some noise or unwanted DC component is added or mixed with the source signal and arrived at the input of this amplifier, what happens? There is no prevention, there is no protection here to block that unwanted noise or DC component. That will automatically enter into the first stage and gets amplified in the first stage, not yet finished. That amplified noise or amplified unwanted DC during AC signal amplification I am talking about. Students, please remember, when AC signal amplification is going on, in case if any unwanted DC component is added or mixed with the input signal and arrived at the input of first stage, that will automatically enter into the amplifier because of direct coupling here, where it gets amplified to certain extent, and that amplified unwanted DC will be directly fed into the second stage. Again it gets amplified there and will be fed into the load. By the time it is fed into the load, it becomes some considerable value of unwanted DC, which can be considered as noise. So noise amplification may be another problem in the circuit. Improper impedance matching is the next drawback of the circuit. Of course, there is no provision or separate arrangement is made in the circuit to match the output impedance of first stage with the input impedance of second stage. We know if both are CE amplifiers, first stage CE amplifier output impedance is around 40 kilo ohms, whereas second stage CE amplifier's input impedance is around 1.1 kilo ohm. That means the output impedance of first stage CE amplifier is not matched with the input impedance of second stage CE amplifier. Unfortunately, in direct coupled amplifier or direct coupled mechanism, no additional precaution is taken or no additional arrangement is made to match the impedance of first stage with the input impedance of second stage. These are the basic drawbacks of this direct coupling scheme. Now, let's look into the advantages and disadvantages of RC coupling scheme or capacitive coupling scheme. If you look at the circuit carefully here, the source signal is coupled to the amplifier by means of a capacitor, and then the output of first stage is coupled to the input of second stage by means of a capacitor. The output of second stage is coupled to the load by means of a capacitor, and so on. That's why this can be called as capacitive coupling or RC coupling. Now, of course, the most popular amplifier in which RC coupling is implemented is two-stage RC coupled amplifier. Two-stage RC coupled amplifier is one of the best example for RC coupling scheme. Yeah. Now, let's consider the advantages of this amplifier first. The first advantage is understandable, excellent isolation of DC conditions, which was missing in direct coupled amplifiers, because everywhere at every stage we are using coupling capacitors between source signal and first stage, between first stage and second stage, between second stage and load also we are using coupling capacitors. Automatically, if any unwanted DC signal is arriving from source signal, that will be blocked blocked by the C11. In case if any DC current or the DC current of first stage, if it is trying to mix with the DC current of the second stage, this C21 is going to separate or block the DC components, and so on. As a result, excellent isolation of DC conditions. If individual stages are being isolated in terms of DC conditions. As a result, the DC conditions of individual stage which we maintain at the time of design can be protected. That is the first advantage of this circuit. Second advantage, of course, understandably, it's an extension for the first one. If the DC conditions are properly isolated, automatically the operating point of the individual amplifier becomes stable. I already explained in the previous direct coupling scheme, we maintain DC base current IBQ for first stage, IBQ1, that will maintain a collector current of ICQ1 here. Similarly, we maintain a DC base current of IBQ2 for second stage, and that will automatically maintain a DC current of ICQ2 as one of the important coordinate of operating point. Since there is proper isolation between stage 1 and stage 2, there is no chance of this DC current of first stage to be mixed with the DC current of second stage. As a result, the DC base current of second transistor Q2 remains as it is. Therefore, the quiescent collector current of second stage remains as it is. That will automatically maintain the operating point at the desired location where it is already established. As a result of this, operating point becomes quiescent or stable. As a result of that, faithful amplification is guaranteed in all RC coupled amplifiers. That's a very good news. Then, signals at a specific range of frequencies can be amplified. Therefore, only desired signals can be amplified. Understandable? If you look at the frequency response of this amplifier, you can easily understand this advantage. Yeah, due to the presence of coupling capacitors, lower cutoff frequency is established. And of course, due to the internal or junction capacitors of BJT, upper cutoff frequency is established. As a result, signals between FL and FH only gets amplified here. Remember, FL and FH are being established by us only intentionally. Because of that reason, the signals of selected range of frequency only or desired signals in the selected range of frequency only gets amplified, which is a mandatory requirement or a desirable feature in any amplifier circuit. Otherwise, unwanted signals may be amplified and that leads to a lot of noise in the resultant output. That can be considered as an advantage here. In this circuit, unwanted signals will never be amplified because lower cutoff frequency and upper cutoff frequency are being selected by us intentionally. As a result, signals between FL and FH only gets amplified. That means desired signals of our interest only gets amplified here. That's an advantage. Then, of course, since capacitor is used as coupling element, if you look at the input stage here, this blocking capacitor I am talking about. In case, for example, when this input signal is arriving from a natural source, assume that some unwanted DC is being mixed with that and arrived at the input terminals of this amplifier. But no problem. We have a blocking capacitor C11 here. This blocking capacitor will stop or block the DC component, or unwanted DC component can be considered as noise here. That noise component can be blocked here. Only the desired AC signal is allowed to enter into the amplifier. As a result, noise amplification is completely avoided in this amplifier. That is another significant advantage of this coupling scheme. In spite of these many advantages, this circuit also suffers few drawbacks. Let us consider those drawbacks also. First one is, of course, DC signal amplification is not possible. Yes, this is already understandable. Because of the blocking capacitor available here, in case if you want to apply a DC input here and if you want the DC input signal to be amplified here, there is no, it is not possible in the circuit. Why? Because at the input level or at the input terminals itself, that DC component will be blocked. So DC signal amplification is not possible in RC coupled amplifiers. And signals at very low frequencies can't be amplified. Of course, this is what already we observed in the previous frequency response. Signals in the very low frequency range, in this frequency range, signals cannot be amplified. Right from F equal to 0 up to FL, all the signals are being rejected. So signals in very low frequency range cannot be amplified. And of course, improper impedance matching is another problem in this circuit also, as we have seen in the previous case also. See, again, if you look at the coupling between two stages, no additional arrangement is made to match the output impedance of first stage with the input impedance of second stage here. No additional precaution is being taken by the designers. As a result, impedance matching is not properly achieved. So this is the another drawback in the circuit. Now, let us consider transformer coupling. See, if you carefully look at this diagram, the output of first stage is coupled to the second stage via a transformer here. if the output of first stage is coupled via a transformer to the input of the second stage. The output of second stage is coupled to the load or to the next stage via a transformer, and so on. That's why this technique is popularly called as transformer coupling. This coupling scheme is popularly called as transformer coupling, and this transformer coupling is mainly used in power amplifiers, namely class A, transformer coupled class A, class B power amplifier, and so on. In all popular power amplifiers, transformer coupled class A power amplifier, class B power amplifier, class B push-pull power amplifier, this type of transformer coupling is implemented. Now let's see the advantages and disadvantages of this scheme. First, let us look into the advantages. Excellent impedance matching, which was missing in the previous two cases, is being achieved here. If you carefully observe, with the help of in conventional amplifiers, we used to have a resistor RC here, which is not flexible for us. We cannot change that resistance as and when we want. In order to match the impedance of first stage with the output impedance of the first stage with the input impedance of second stage, there was no facility in the previous two circuits. But here, when we use a transformer in the load section of first stage, simply what we can do is by changing the number of turns at the primary and secondary, we can see that the output impedance of first stage and the input impedance of second stage can be easily matched. So it's a matter of proper selection of number of turns at the primary and number of turns at the secondary will help us to match the output impedance of first stage with the input impedance of second stage. As a result, impedance matching is very much possible in transformer coupled amplifiers. Second one, signals at a specific range of frequencies can be amplified to a high gain. Now if you look at the frequency response of this amplifier, you can easily understand that. Frequency response of transformer coupled amplifiers can be shown like this, where signals at a very specific range of frequencies or less range of frequencies only can be amplified, but with high gain they are amplified. As a result, only specific range of frequencies or signals in very specific range of frequencies of our desired or of our interest can be amplified with a maximum amount of gain. That is the advantage of this circuit. Next, power consumption is very less in the amplifier, therefore DC to AC conversion efficiency of the amplifier is very high. Let us try to understand this. This is one of the very important advantage of transformer coupling. See, in conventional amplifiers, we used to have a resistor RC here. At the load, we used to have a load resistance RC. Then the problem in conventional amplifiers is, when this BJT is drawing power, DC power from power supply, the load resistance RC, collector load resistance RC will waste considerable amount of power. Lot of power, almost 50% of the power, DC power gets wasted across that collector load resistance used in conventional amplifiers. But in transformer coupled amplifiers, we are not going to use any resistance in the load section. Instead of that, we are using a transformer. Then what happens? Whenever DC current is being flowing, whenever this VCC is supplying a DC current into the BJT, this primary winding simply act like almost a short circuit. As a result, no DC power is wasted at the collector load. As a result of that, entire DC power given by the supply can be drawn by the BJT, which can be later on converted into AC. As a result of that, excellent DC to AC power conversion efficiency in power amplifiers, in transformer coupled amplifiers, unlike the conventional amplifiers. In conventional amplifiers, the problem is the DC to AC power conversion is just 25%. That's what mathematical results are telling us, experimental results are telling us. Whereas in transformer coupled amplifiers, right from 50% to almost up to 95%, we can improve the DC to AC conversion efficiency. That's a great advantage of this circuit. That's why this transformer coupling is very much preferred in power amplifier circuit, where DC to AC power conversion efficiency is an important parameter. Now let's see the disadvantage of this circuit. Humming of transformer may be delivered in the form of noise into the load. Understandable, of course. Whenever you observe the transformers when they are under operation, transformers used to make sound. That is popularly called as humming of transformer. That sound made by the transformer, when first stage and second stage are coupled by means of a transformer, output of the amplifier second stage is coupled to the load also by means of a transformer. Whatever the sound or humming, technically speaking, humming made by the transformer also will be delivered into the load in the form of noise. That is the basic drawback of this circuit. And of course, the other one is the transformer which we are using as coupling element is of course very large in size and is costly. These are the disadvantages of transformer coupling scheme. Now let's consider the last coupling scheme, inductor coupling or tuned circuit coupling. Now, if you carefully observe here, the output of first stage is connected to the second stage via an LC tuned circuit, hence the name tuned circuit coupling is given for this. Similarly, the output of second stage is coupled to the next stage or load via another LC tuned circuit, hence the name tuned circuit coupling. And this type of coupling scheme is mainly used in tuned amplifiers, class A tuned amplifier, single tune, double tune amplifiers. We will be using this kind of coupling scheme. Now let's see the advantages of this circuit, this coupling scheme. The first advantage is signals at a specific range of frequencies can be amplified to a maximum extent. Understandable? If you look at the frequency response of this amplifier, you can understand this. This is the frequency response of an LC coupled or a tuned circuit coupled amplifier, where signals at a specific frequency, popularly called as operating frequency or resonating frequency or central frequency, will be amplified to a maximum extent, and below that, above that, all the signals are rejected. So signals at a specific frequency or very narrow range of frequencies only gets amplified. So this kind of technique, tuned circuit coupling, is very much used in TV receivers, TV and radio receivers. We need this kind of, whenever we want to select a channel in a TV, that means only one frequency to be amplified to maximum extent, remaining all the frequencies are to be suppressed. And exactly that facility is there in tuned circuit coupling. We will be using these tuned amplifiers or tuned circuit coupled base amplifiers in TV receivers and radio receivers. Second advantage of this circuit is, of course, proper isolation of DC conditions among individual stages. Understandable, as there is a coupling capacitor available between first stage and second stage, between second stage and third stage and so on. Proper isolation of DC conditions is possible. All the individual DC conditions of individual amplifiers can be properly maintained or separately maintained without any mixing of DC conditions from stage 1 to stage 2 or stage 2 to stage 3 and so on. As once the DC conditions are properly isolated, that leads to operating point stability. That means individual amplifiers operating point where it is already established remains there only. Therefore, there won't be any shift in the operating point. If there is no shift in the operating point, faithful amplification is always guaranteed in amplifiers. Best example again, class A tuned amplifier. In class A tuned amplifier, operating point is actually set at the center of active region. Therefore, the full cycle of output signal is possible without any clipping or without any distortion. So that is the advantage of this circuit, another advantage of this circuit. Now let's look into the disadvantages of this circuit. Very narrow bandwidth. Of course, just now we have seen the bandwidth of this amplifier is very narrow. In fact, only one frequency or maybe very narrow range of frequencies only gets amplified. So understandable, bandwidth is very narrow. That is one that may be considered as one drawback. And of course, the inductor which we use as coupling element here is large in size. then whenever we want to fabricate this circuit in integrated circuits, these inductors are not going to be compatible with IC design. As inductors are large in size, it's not possible for us to fabricate them in integrated circuits. So these are not compatible for these inductor coupling is not compatible for IC design. So these are the drawbacks of the circuit. This is how you need to answer that question, students. If the question is explain the merits and demerits of various coupling schemes used in the amplifier circuits, then this question was asked in various university examinations. So the merits, first what you do is draw the circuit, show that this is how you need to draw direct coupling scheme. This is how we need to draw RC coupling scheme. This is how you need to draw transformer coupling scheme. This is how we need to draw tuned circuit coupling. First draw the circuits neatly, then explain the advantages and disadvantages one by one neatly. Then you will get full marks in that question. Right. Now let us see one more question that is being asked repeatedly in the previous various university examinations. That is, draw the circuit of high input resistance amplifier using Darlington pair configuration, and with necessary equations explain how this amplifier can be used as voltage buffer in practical applications. This is this question was asked number of occasions in various university examinations. One of the most important question for university examinations. Now let us see how we can deal with this circuit. This is the basic circuit of Darlington pair amplifier. A pair of transistors are available in the form of a package, and hence this is popularly called as Darlington pair. These two together available in the form of a single package, hence this is called Darlington pair. And with the help of the Darlington pair, if you construct an amplifier, such an amplifier is called as Darlington pair amplifier, or simply you can call it as, because if you carefully observe, input signal is applied to the base of first stage and output is obtained at the at the emitter of second stage of the first stage. So first stage is a CC amplifier, common collector amplifier. Similarly, input signal is applied at the base of second stage and output is obtained at the emitter of second stage. This is also another CC amplifier. So this can be considered as a CC direct coupled amplifier, or popularly called as Darlington pair amplifier. Now in order to explain how a Darlington pair amplifier can be used as a voltage buffer in real-time applications, you have to analyze the total amplifier. You have to analyze the total amplifier, and finally you have to obtain equations for voltage gain, input resistance and output resistance in this amplifier. Overall voltage gain, overall input resistance and overall output resistance equations you are supposed to obtain. After obtaining the equations for overall voltage gain, input resistance and output resistance, we have to compare those values with the qualities or requirements of an ideal voltage buffer. We know for an ideal voltage buffer, the requirements are unity voltage gain, infinite input resistance and zero output resistance are the requirements of an ideal voltage buffer. Then you have to prove that in this Darlington pair amplifier, the overall voltage gain is near to unity, overall input resistance is very high, overall output resistance is very low. That's what you are supposed to prove. Once you prove that, you can simply say that because Darlington pair amplifier has got very high input resistance, very low output resistance and the voltage gain is near to unity, we can use it as a voltage buffer in real-time application. This is how you need to answer this question. Now what we should do, we should analyze this amplifier completely stage by stage. Now first I will show you the small signal model. We know we cannot analyze an amplifier directly from its basic circuit. We have to obtain the small signal model of the total amplifier. As already you have studied small signal model analysis in Continue. Yeah. See, after analyzing the second stage, you go to the first stage. See, we know we can estimate the load resistance of first stage after knowing the input resistance of second stage. Then once you know the load resistance of the first stage, you can simply analyze the first stage for the 4 reference parameters, namely voltage gain, current gain, input resistance and output resistance. Now let's consider the analysis in step by step. Yeah, as I told you, first I have started with second stage CC amplifier. In CC amplifier, in each stage, within 5 steps, we can complete the analysis. Within 5 steps, we can finish off the analysis. The 5 steps are meant for, first step is for load resistance, second step is for current gain, third step is for input resistance, fourth step is for voltage gain, and fifth step is for output resistance. So let us start with the load resistance. Step 1. As we are talking about second stage, for every parameter I will use a suffix 2. RL indicates load. For second stage, that's why I called it as RL2. Yeah. Now look at the circuit. RL2 is nothing but RE. Load resistance of the second stage, which is available in the circuit, is RE. So RE itself is the load resistance. Once we estimate load resistance in any amplifier, we are in a position to estimate current gain. So let us start with second step, current gain. What is the general formula for current gain? In any amplifier circuit, current gain means output current by input current. Since we are talking about second stage here, I will write it as I02 by II2. Then if you look at the circuit carefully, I02 means minus IE2, II2 means IB2. So we can write it as minus IE2 by IB2. For this, we need to obtain an equation. To obtain an equation for current gain, what you do is just go back to the circuit. Look at the small signal model here. At this emitter node, apply a KCL. See, what is KCL? Sum of the currents entering a node should be equal to sum of the currents leaving the node. What is the current entering into node E2? IE2 is the current entering. Then 2 currents are leaving from this node E2. One current is this one. HFC IB2 is one current. And the other current is current into this 1 by HOC. Means VE2 by 1 by HOC. That means VE2 into HOC. So KCL at node E2 should be IE2 equal to HFC IB2 plus HOC VE2. That's what we should write here. KCL at node E2. will give us IE2 equal to HFC IB2, just now I have explained this, plus HOC VE2. Now again look at the previous slide. We know VE2 is nothing but voltage across load. That means it can be given as minus IE2 into RE or minus IE2 into RL2. VE2 from the output section of the circuit, if you carefully observe, it can be written as minus IE2 into this resistance, load resistance RL2. I will use that relation here. But from the output section of the circuit, VE2 equal to minus IE2 RL2 or RE. I will use this relation in this equation, which will give us IE2 equal to HFC IB2. First term remain as it is, minus HOC into IE2 RL2. Just I have substituted VE2 equal to minus IE2 RL2 in the above equation, which gives us IE2 equal to HFC IB2 minus HOC IE2 RL2. Then what we do is, let us transfer this minus HOC IE2 RL2 to left hand side and take IE2 common. I will transfer this minus HOC IE2 RL2 to left hand side and I will take IE2 common. That gives us IE2 into 1 plus HOC RL2 equal to HFC IB2. Then bring this IB2 to left hand side, which gives us IE2 by IB2 equal to HFC by 1 plus HOC RL2. But if you look at equation 2, current gain is not IE2 by IB2, it is in fact minus IE2 by IB2. Therefore, we can write the equation for current gain as AI2 equal to, which is minus IE2 by IB2 equal to minus HFC by 1 plus HOC RL2. This is the equation for current gain. Accurate equation for current gain is this. However, we know 1 plus HOC RL2. Since HOC is very small, which is in the range of micro amps per volt, it is in the range of 10 power minus 6. That means HOC into RL2 is always much smaller than 1. Therefore, this current gain can be approximated to minus HFC. And by using the conversion equations, H parameter conversion equations we already studied in the subject called EDC, HFC itself is minus of 1 plus HFE. So, we can write it as just 1 plus HFE. This is the complete analysis for current gain of the amplifier. Do you understand? This is the complete analysis of current gain, complete analysis for current gain. Simply what I have done is, in the circuit, I have applied KCL at node E2. and I got an equation called IE2 equal to HFC IB2 plus VE2 into HOC. That is the equation I got. Then I have replaced VE2 with minus IE2 into RL. That is the second work I have done, and then a simple mathematical manipulation I have done, nothing more than that. So that gives us overall current gain. Accurate equation is minus HFC by 1 plus HOC RL2, or approximately we can write it as 1 plus HFE. This is the analysis for current gain. Now, once after estimating load resistance and current gain, we are in a position to estimate input resistance. Let's go for the next step. Step 3. Input resistance. Of course, input resistance is VI2 by II2, general formula. For second stage, for any amplifier, input resistance means VI by II. We are talking about second stage, so therefore it will be VI2 by II2. Because we are working with CC amplifier, input is VB, so it is VB2 by input current is IB2, so VB2 by IB2. This is the equation we are supposed to use. For this also some little work we are supposed to do in the circuit. Let's go back to the circuit. Yeah, here, this is what I was talking about. We are actually estimating input resistance from here in this direction. Here we are estimating this input resistance. This input resistance is nothing but VB2 by IB2. That's what I wrote there in that equation. Now, for the estimation of input resistance, simply what you do is you apply a KVL in the input loop. Apply KVL in the input loop, which gives us, look at this, VB2 equal to HIC IB2 plus HRC VE2. That is the KVL. So, I will write that equation there. KVL for input loop. Gives us VB2 equal to HIC IB2 plus HRC VE2. That is the equation we obtain by applying KVL for input loop. Then simply what you do is you rewrite this equation as HIC IB2 plus HRC. We know in the previous analysis we have already obtained VE2 equal to minus IE2 RL2. I will use this relation in that equation. VE2 equal to minus IE2 RL2 relation is already there with us. Let us use this relation in this equation. This is minus IE2 into RL2. This is for VE2. Now, what is RI2? RI2 is VB2 by IB2. So, what I do is I will divide the total equation with IB2. So, therefore, RI2, which is equal to VB2 by IB2 equal to, when I divide this first term with IB2, it gives us HIC only plus HRC into minus IE2 into RL by IB2. But we know minus IE2 by IB2 is nothing but AI, current gain. Just before this we have estimated that. That means we can rewrite this equation as HIC plus HRC into AI2 RL2. This is the reference equation for input resistance. Accurate equation for input resistance is this. Ri2 is HIC plus HRC AI2 RL2. Here also if you carefully observe, simple procedure which I have followed is, we know Ri2 means VB2 by IB2. Just I have applied KVL for the input loop in the circuit, where VB2 equal to HIC IB2 plus HRC VE2. That is the equation I got. And in that equation some simple mathematical manipulations I have made, where I have replaced this VE2 with minus IE2 RL2. Then I have divided the total equation with IB2. That gives us Ri2 equal to HIC plus HRC AI2 RL2. However, we can go for some approximations here. According to conversion equations, HRC is 1. Therefore, I can rewrite this equation as Ri2 equal to HIC plus, of course, HRC is 1. So, I am just writing it as 1 into AI2 RL2. From this, I will write an equation for AI2 RL2 which is required for me in the next level. From this, I am writing AI2 into RL2 equal to Ri2 minus HIC. This is required for us in the next level. So, for time being, let us keep this equation aside. We will be using this equation at a later stage. I will recall this equation at a later stage. Yeah, hope you understand the analysis for input resistance, students. Now, once after estimating load resistance, current gain and input resistance, we are in a position to estimate voltage gain of the amplifier. Let's do that. Step 4. Voltage gain. AV2 equal to, of course, in any amplifier, voltage gain means output voltage by input voltage. Since we are talking about second stage, so I am writing it as V02 by Vi2. So this is, of course, V02 means VE2, Vi2 means VB2, where VE2 is minus IE2 RL2. Already we got this equation. And similarly, VB2 means IB2 into Ri2. But we know minus IE2 by IB2 is nothing but current gain. So, we can rewrite this equation as AI2 RL2 by Ri2. Another important equation. This is the equation for voltage gain. Accurate equation for voltage gain is this. However, we can simplify this equation for our future requirement. That is, let's go back to the previous equation 3b here. AI2 RL2, we got it as Ri2 minus HIC. I will use that relation in the present case. Since AV2, we got it as AI2 RL2 by Ri2 is the formula we got as accurate equation. And as I just now told you, AI2 RL2 equal to Ri2 minus HIC. That relation I am using here. So this gives us Ri2 minus HIC by Ri2. In other words, we can write it as 1 minus HIC by Ri2. But if you have the minimum knowledge of H parameters, HIC is nothing but HIE. HIE is just 1100 ohms, whereas Ri2 in CC amplifier is generally in the range of mega ohms. So, HIC is in the range of just ohms, Ri2 is in the range of mega ohms, therefore, this term is very small. when compared with 1. As a result, we can approximate the voltage gain in CC amplifier second stage as 1. Very important point, students. Try to remember this. Overall voltage gain of second stage CC amplifier is approximately equal to 1. This is about voltage gain. Then coming to the next parameter, output resistance. Step 5. Output resistance. R02. Let's go back to the circuit. Here, estimation of output resistance is to be done by looking into the amplifier here. Carefully observe this. Exactly here we are supposed to estimate the output resistance. Now if you carefully observe the circuit, R02 is nothing but VE2 by IE2. VE2 by IE2 is the equation for that. So I will write it as R02 equal to VE2 by IE2. But whenever we estimate output resistance in any electronic circuit, there are two very important conditions we are supposed to implement. The two conditions are, to avoid the loading effect, we have to remove the load from the circuit while estimating output resistance. The first most important work which we are supposed to do is, to avoid loading effect caused by the externally connected load, we have to remove the load. So load must be open. First rule, with load open. And the other one is to avoid the effect of input parameters, input independent parameter on the output parameters. We have to set input voltage 0. Means VB2 is supposed to be set 0. These are the two conditions we are supposed to implement while estimating output resistance. Not only in the circuit, in any amplifier circuit while estimating output resistance, two conditions. One is load must be open, and second one is input voltage should be set 0. So load open, VB2 0 are the two conditions. We will be using those two conditions at a later stage for the to complete the analysis here. See, for mathematical convenience, instead of estimating R02, first I will estimate admittance Y02. Finally, I will calculate output resistance, just for mathematical convenience only. This implies Y02, of course, nothing but 1 by R02 means IE2 by VE2. But I hope you remember, in the previous, while estimating current gain, we got an equation for IE2. If you look at this equation, this is what I was talking about. I will be using this equation there as it is. IE2 equal to HFC IB2 plus HOC VE2 is the equation available with us. I want to use this equation there. So this is HFC IB2 plus HOC VE2. This is for IE2. By VE2 as it is, let us substitute. This gives us, I will write the second term first because VE2 gets cancelled in the second term. I will write second term first, HOC plus HFC into IB2 by VE2. Let it be. I will come back to this equation at a later stage. Till this extent, try to understand, students. Simply what I have done is, I wrote the general equation for output resistance as VE2 by IE2, where the two important conditions are considered as load open, input voltage 0. Then what I have done is, for mathematical convenience, I am trying to estimate output admittance rather than output resistance. At a later stage, I will take the reciprocal value, don't worry about that. So Y02 equal to 1 by R02, that is IE2 by VE2. IE2, we have an equation for IE2. We have applied KCL at node E2 and we got this equation, and I have used that equation as it is. Then Simply in second term VE2 gets cancelled. So I wrote second term as HOC and in the first term HFC into IB2 by VE2. Let it be. Now consider equation for VB2 we got by applying KVL for input loop. I hope you remember. I will show the circuit one more time. By applying loop equation KVL here, we got an equation for VB2. That is VB2 equal to IB2 into HIC plus HRC VE2. I will be using that equation here now. Consider VB2 equal to HIC IB2 plus HRC VE2. This is the equation available with us. But if you carefully observe, one of the important condition is VE2 equal to VB2 equal to 0. That means this VB2 should be set to 0. From this, we can rewrite this equation as HIC IB2 equal to minus HRC VE2. What is the parameter actually we need? IB2 by VE2 is required. So transfer this VE2 to left hand side and take this HIC to right hand side. This gives us IB2 by VE2 equal to minus HRC by HIC. Now let us substitute this equation 5b in equation 5a. This equation I will substitute in this equation, which gives us equation 5b in equation 5a. Equation 5a is Y02 equal to HOC plus HFC into IB2 by VE2. Just now in 5b we got IB2 by VE2 equal to minus HRC by HIC. Let us substitute that in that equation. Y02 equal to HOC minus HFC HRC by HIC. This is the accurate equation for output admittance. This is the accurate equation for output admittance. However, let us go for some approximations here. We know HOC is HOE according to conversion equations. Minus HFC is 1 plus HFE according to conversion equations. HRC is 1 according to conversion equations and HIC is HIE. Now if you carefully observe, HOE is very small. It is almost equal to 0. That's why I can approximate this equation to 1 plus HFE by HIE. This is Y02 please. But what is the parameter actually we are trying to estimate? Output resistance. That means let us write the equation for output resistance now. Output resistance of the second stage equal to 1 by Y02 means 1 by of this value, which gives us HIE by 1 plus HFE. Another important equation. This is the equation for output resistance in second stage CC amplifier. With this, we have completed the analysis of current gain, input resistance, voltage gain, output resistance, which are the four reference parameters in stage 2. Exactly by following the same procedure, we have to estimate all these four parameters again in stage 1. That is the work we are supposed to do in case 2. Luckily, good news is First stage is also a CC amplifier. Instead of deriving these equations again and again, what I do is I will just list out all the final equations for first stage as easily by following the same procedure. Case 2. Analysis of first stage analysis. First stage is also a CC amplifier. So, since just now we have completed the second stage analysis, which is a CC amplifier, by following the same procedure, we can easily estimate the 4 reference parameters in first stage also. So, instead of going for the derivations, I am just giving you the final equations here. Step 1, load resistance. Load resistance in first stage is simply equal to input resistance of second stage. Then current gain in first stage is AI1 equal to I01 by II1 means minus IE1 by IB1, which gives us minus HFC by 1 plus HOC RL1. This is the accurate equation, as we have already approximated this to minus HFC, which is equal to 1 plus HFE. Then step 3, input resistance. RI1 equal to VB1 by IB1 is the formula, and the equation for this is HIC plus HRC AI1 RL1 is the accurate equation, which can be approximated to HIC plus AI1 RL1. This is the equation for input resistance. Then step 4, voltage gain, which is VE1 by VB1. It should be equal to AI1 RL1 by RI1 is the accurate equation, and this can be approximated to 1 minus HIC by RI1, which can be approximated to 1. Then finally, output resistance. Output resistance of the first stage R01 equal to VE1 by IE1 is the formula, and is given by HIE by 1 plus HF. These are the set of equations which gives us the current gain, input resistance, voltage gain and output resistance in case of first stage. Now with this, in first case we have estimated the 4 reference parameters: voltage gain, current gain, input resistance and output resistance in stage 2. In case 2, we have estimated the 4 reference parameters: voltage gain, current gain, input resistance and output resistance in stage 1. Now with the help of these set of equations, 4 equations in the previous case and 4 more equations in the present case will help us to estimate the overall performance of the amplifier. Let's go for that. Case 3. Overall analysis. Let us start with voltage gain first. Step 1, let us start with overall voltage gain. I will write it as AV. Of course, AV, overall voltage gain, means general formula is V0 by Vi. That means second stage output voltage is VE2 by first stage input voltage is VB1. That means, of course, VE2 by VB1, there is no ready-made formula for this for us. That's why what I do is, I will do a simple modification. I will divide and multiply the equation with VE2 by VB2 into VB2 by VB1. I repeat, in the Darlington pair amplifier, second stage output voltage is VE2, first stage input voltage is VB1. That's why V0 by Vi, I have replaced that with VE2 by VB1. But we don't have any formula for VB2 by VB1. That's why for further requirements, what I do is, I will divide and multiply this equation with VB2. Then we know VE2 by VB2 is nothing but AV2. We already estimated this. This is AV2 into VB2. If you look at the circuit diagram, look at this. VB2 is nothing but VE1. Both VB2 and VE1 are in parallel. So I can replace VB2 with VE1. Hope you understand this. VB2 and VE1 are exactly in parallel. So we can replace VB2 with VE1. So that's what I am doing now. This is VE1 by VB1. Good news is, we have a formula for VE1 by VB1. VE1 by VB1 is nothing but AV1. So therefore, this is AV2 into AV1. Already we got the equations for AV2 and AV1. We know AV2 is 1, AV1 is also 1. So this is now approximately equal to 1. This is the overall voltage gain in Darlington pair amplifier. Overall voltage gain in Darlington pair amplifier is approximately equal to 1. Then step 2. Let's estimate input resistance. Overall input resistance in any amplifier, overall input resistance means in any multi-stage amplifier, overall input resistance is nothing but input resistance of the first stage. That is Ri equal to Ri1. But Ri1, we got an equation for this. This is HIC plus AI1 RL1. This is, if you carefully observe, I will go for conversion equations. HIC is nothing but HIE. AI1 approximate equation is 1 plus HFE. And RL1 is Ri2. Now if you carefully observe this equation, if HFE is 100, 1 plus HFE is 101, Ri2 is minimum of 2 mega ohms in CC amplifier. 2.04 mega ohms is the input resistance in second stage. Second stage is a CC amplifier. In Darlington pair amplifier, second stage is a CC amplifier. In an individual CC amplifier, input resistance is around 2.04 mega ohms. This is what we have already studied in a subject called EDC while analyzing CC amplifier. So, in individual CC amplifier, second stage CC amplifier, input resistance is 2.04 mega ohms into 101. 101 into 2 mega ohms means around 202 mega ohms is a huge amount of input resistance. Very high amount of input resistance. Then finally, let's talk about output resistance of the amplifier. The total output resistance in any multi-stage amplifier is always equal to the output resistance of the last stage. Means, in the present case, second stage. Second stage output resistance is the output resistance of the total amplifier, R02, which is obtained as HIE by 1 plus HFE. This is what the equation we got. Now if you carefully observe, if you recall the typical values here, HIE is 1100 ohms, HFE is 50, let us say, 51, 1100 ohms by 51. This is around 50, HIE is around 1100 ohms. This 1 plus HFE is 51. This will give us around 21.56 ohms. 21.56 ohms. Therefore, if you consider all the three parameters we got now, voltage gain is approximately unity. Overall input resistance is very high, in the range of hundreds of mega ohms. Overall input resistance just 21.56 ohms means very low. Now let's compare these three parameters of Darlington pair amplifier with the characteristics of voltage buffer. I will consider voltage buffer as reference here. Let us consider voltage buffer. For an ideal voltage buffer, the characteristics are of an ideal voltage buffer are AV should be 1, RI should be infinite, R0 should be 0. This is about an ideal voltage buffer. Versus Darlington pair amplifier, let us consider now. Just now we have completed the analysis of Darlington pair amplifier and we got its voltage gain as 1, its input resistance as very high, its output resistance as very low. The characteristics of Darlington pair amplifier are AV is approximately equal to 1, input resistance is very high, and output resistance is very low. Now, if you look at the characteristics of Darlington pair amplifier, since Darlington pair amplifier has very high input resistance, it is popularly called as high input resistance amplifier, and because it has three characteristics AV equal to 1, RI equal to very high, R0 equal to very low, which are much close to the characteristics of a voltage buffer. That's why Darlington pair amplifier is very popularly used as a voltage buffer in real-time electronic circuits. This is how you need to answer this question. The question was, draw the circuit of high input resistance amplifier using Darlington pair and with necessary equations explain how it can be used as a voltage buffer in real-time electronic circuits. That was the question which we have considered. To answer that question, what you need to do, you have to analyze second stage first in the case 1, first stage in case 1, case 2 you have to analyze first stage. Then in case 3, you have to do the complete analysis, overall analysis, and by completing the overall analysis, with the results of overall analysis, you need to compare the characteristics of Darlington pair amplifier with the characteristics of an ideal voltage buffer. Because the characteristics of Darlington pair amplifier are much close to the characteristics of ideal voltage buffer, we can claim that Darlington pair amplifier can be used as a voltage buffer in real-time electronic circuits. I hope you understand, students. By following the same way, same procedure, you can analyze two-stage RC coupled amplifier. You can also analyze CE-CB cascode amplifier. These are the three important multi-stage amplifiers that are there in the syllabus of multi-stage amplifiers in every university syllabus. Doesn't matter whether it is JNTU Hyderabad or other universities also. The same syllabus will be there. That is, the three possible the three possible multi-stage amplifiers are Darlington pair amplifier, two-stage RC coupled amplifier, and CECB cascode amplifier. Good news is, in all the three amplifiers, the analysis procedure is exactly the same as we have done in the case of Darlington pair amplifier. Follow the same procedure and you try to analyze the two-stage RC coupled amplifier and CECB cascode amplifier as an exercise. Yeah. Now, let's see one problem in this related to these multi-stage amplifiers. The question is, 8 identical amplifiers, each having lower cutoff frequency of 10 Hz and upper cutoff frequency of 10 MHz are cascaded. Then estimate overall bandwidth of multi-stage amplifier. I repeat, the question is, 8 identical amplifiers, each having lower cutoff frequency of 10 Hz and upper cutoff frequency of 10 MHz are cascaded. Then estimate the overall bandwidth of the total multi-stage amplifier is the question. Now, let's see how to answer this, how to solve this problem. Remember, while answering or while solving any problem in university examinations, before you directly make an attempt to solve the problem, first what you do is, you just list out the data given by the examiner neatly. So means given data. What is the data given for us? Look into the question one more time. 8 identical amplifiers. If you look at the first line in the question, 8 identical amplifiers. So, information, 2 important points are available in this information. They are identical stages is mentioned by the examiner. This is one clue for us. Identical stages are cascaded. Second information available for us is N means number of stages is 8. Identical stages is one information available. N means number of stages is 8 given by the examiner. Then lower cutoff frequency of each amplifier having lower cutoff frequency of 10 Hz and upper cutoff frequency of 10 MHz means FL1 of individual amplifier is 10 Hz. FH1 means upper cutoff frequency of individual amplifier is 10 MHz. This is the information available, and the parameter which we are supposed to estimate is, examiner is asking us to calculate bandwidth of the total multi-stage amplifier. Overall bandwidth of multi-stage amplifier, bandwidth of 8-stage amplifier. We are supposed to estimate. This is the information available. Understand? The available information for us is identical stages is one information provided by the examiner. Number of stages 8 given by the examiner. Individual amplifiers lower cutoff frequency is 10 Hz and individual amplifiers upper cutoff frequency is 10 MHz. Then we are supposed to estimate the total bandwidth of the amplifier. Remember, for the estimation of this bandwidth, the reference formulas which we are supposed to use, I will list out here. Reference formulas we are supposed to use here are overall, first one is overall lower cutoff frequency of multi-stage amplifier. Overall lower cutoff frequency. Popularly represented as FL power n equal to FL1 by under root 2 power 1 by n minus 1 is one formula available for us. This is one equation we are supposed to use. Second one, overall upper cutoff frequency. FH1 formula is FH power n is the formula we are supposed to use. Overall upper cutoff frequency is popularly represented as FH power n, where FH power n is given with an equation FH1 into under root 2 power 1 by n minus 1. This is another equation we are supposed to use. And then finally, the parameter of our interest. Examiner is asking us to calculate overall bandwidth. Overall bandwidth formula is FH power n minus FL power n. These are the set of equations. This is one equation we are supposed to use. This is the second equation we are supposed to use, and this is the third equation we are supposed to use for the estimation of bandwidth. Now let's use these equations one by one and let's try to get the solution for in this question. Now, step 1. FL power n equal to FL1 by under root 2 power 1 by n minus 1 is the formula. This gives us FL1 is given as 10 hertz, by under root 2 power 1 by 8 minus 1. Then by simplifying this, you will be getting it around 33.24 hertz. Overall lower cutoff frequency of the multi-stage amplifier, you will be getting it as 33.24 hertz. Then similarly, overall upper cutoff frequency FH power n equal to FH1 into under root 2 power 1 by n minus 1 is the formula. Now in the present case, FH1 is given as 10 megahertz into under root 2 power 1 by 8 minus 1 will give us around 3.008 megahertz. Understand? FL power n overall lower cutoff frequency is FL1 by under root 2 power 1 by n minus 1. Simply I have substituted FL1 given as 10 hertz, FL2 n is given as 8, so it is under root 2 power 1 by 8 minus 1. This gives us 33.24 hertz, whereas overall upper cutoff frequency is FH power n and is given by FH1 under root 2 power 1 by n minus 1 is the formula. So simply FH1 given as 10 megahertz in the question itself, under root 2 power 1 by 8 minus 1 will give us 3.008 megahertz. Then finally, bandwidth. Step 3. Bandwidth, overall bandwidth formula is FH power n minus FL power n. This gives us 3.008 megahertz minus 33.24 hertz, which will come around 3 megahertz. These kind of problems you can expect in the university examinations. So this is how you need to solve these problems, by using set of equations. That's all. We will meet in the next session in the coming days.